Hello Year 7, welcome to this lesson. Before starting our lesson on squares and cube roots, let's do the answer to the puzzle from last lesson. So the puzzle was we had 100 light switches all in a row, and we had 100 people. The first was going to flick every light switch, the second person every second light switch, the third person every third light switch, and so on till all 100 had been through. We wanted to know how many were on. So what we'll do, we'll just look at the first 10 light switches here, and I'm just going to put the numbers above them. And let's just have a look at what happens when the first 10 people go through. Here's person 1. They go through to every single light switch, like so. Person 2 will go to every second light switch, like this. Person 3 to every third, and you can see the multiples of 3 there of course. Person 4 to every fourth, 12's too big. Person 5 to every fifth, 6 here, 7 here, 8 here, 9 here, and 10 here. And let's have a look at what's happened. So, switch 1 started as off, person 1 turned it on, and then it just stayed on because there was no one else there to change the switch. This one here, person 1 turned it on, person 2 turned it off. Person 1 turned it on, person 3 turned it off. Person 1 turned it on, 2 turned it off, 4 turned it back on. Person 1 turned it on, person 5 turned it off. Person 1 turned it on, person 6 turned it off, person 2 turned it off, person 3 turned it back on, and person 6 turned it off. And I just realized that I should have put a little cross there because person 5 actually turned it back off, and person 1 turned it on. So on and off, on and off, and back on and off, on, off, and on, off, on, and off. So we can see that switch 1 is on, switch 4 is on, and switch 9 is on. The reason for that is if you have a look, you can see people turning them on and off actually kind of did it in pairs. So let's take a look, for example, at switch 6. Person 2 turns it on and 3 turns it off. And 2 times 3 is 6. Person 2 turns 8 off and 4 turns 8 on. And person 2 turned this off and 3 turned it back on. But you can see here all the factors coming in pairs. And one part of the pair turns it on, one part of the pair turns it off. But switches 1, 4, and 9 are special because person 1, well, they don't have anyone to pair up with. Same with person 2, because 2 times 2 is 4, so they've got no one to pair up with. And same with person 3 here in 9, because 3 times 3 is 9. 1 and 9 pair up to make a 9 when they multiply together, but 3, well, I need to times 3 by itself to get to 9, and I've only got 1 3. So you can see the switches that are on are the ones with an odd number of factors. But what sort of numbers have odd numbers of factors? Well, of course, that's the square numbers, because if it's a square number, that's square root. Well, that doesn't have a factor to cancel out with, but all the others do. So we know that the square numbers are on, and we also know the square numbers are 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. And of course that means in the end there are 10 switches are on. 10 switches on. So there you go. That's that answer to that puzzle. Okay, so on to our square roots. Now I'm asking, what's 6 times 6? Well, you guys know we can write it as 6 squared from before, and that's of course 36. Now this here, you've probably seen it before, but this symbol means the square root. This is the square root symbol, and it means what number would I have to times by itself to get to 81? And I'd go, well, 9. The answer's 9, and I'll just use a different color for that. The answer's 9. 9 is the square root of 81, and that's because 9 times 9 equals to 81. Now this is a little bit of a tricky one, okay? I've said if x squared equals to 9, what's x? And you think, well, what number do I times by itself to get to 9? And you probably know it's 3. So you go x equals to 3. And then you go, well, hang on a second. What if I got minus 3? If I have x equals to minus 3 times minus 3 is 9, because 2 minuses make a positive. And I've actually got two different answers here. Does this mean I need to go back and put 2 different answers for my 9? Well, no, because if you've got this square root sign over a number, that means we just take the positive one, okay? So if I had something like this, and I've got, if x squared is 7, what's x? Well, I know that x could equal to whatever the root 7 is. We call that just root sometimes. But we also know x could equal to the negative version of root 7. But if I just write my root 7 by itself, so if I've just written this root 7 by itself, it's positive. If I want to make it negative, I actually need to write that negative sign out the front. And I just want to add one more question to this list. I'm going to ask you, what is and the square root of negative 100? And you see 100 there, and you go, well, it feels like it's 10 because 10 times 10 is 100. But 10 times 10 is 100, not negative 100. So, well, it's a negative. Maybe it's minus 10. Minus 10 times minus 10. Wait, that also equals to 100 because 2 negatives are a positive. So the trick is here, if you've got a negative sign underneath your square root, you actually can't find it, okay? It's what we call an imaginary number, so we can't actually take the square root of a negative. Alright, next one. Oops, before that, the cubed roots. So we're going to find what is 2 times 2 times 2. And of course, you guys probably all know this by now, but it's 2 cubed or equals to 8. This one, the cubed root of 125. So for a cubed root, I put a little 3 down there, okay? And I put this little 3 down here, and it says I want a number I times by itself 3 times to get to 125. Pause for a second and have a think about that if you like. But hopefully you can see the answer is 5. The answer's 5, and that's because 5 times 5 times 5, 3 times is 125. What about the cubed root of 7? What number do I times by itself 3 times to get to 27? Take a moment to think about it. Pause the video if you want. And hopefully you can see that it's 3. But here's an interesting one. What about minus 27? Well, I can't take the square root of a negative because I can't times anything by itself 2 times and get a negative number. But what about a cube root? What if I did minus 3 times by minus 3 times by minus 3? Well, that's actually going to work because look, minus 3 times minus 3 is 9, and then I times that by minus 3, and I get 9 by minus 3, and there's that negative 27 just like I wanted, okay? So I can take a cube root of a negative number, just not a square root. I'll let you have a bit of a think about what happens if I want to take a 4th root or a 5th root. Okay, We're now going to try to find the square root of a large number without a calculator. And you might be thinking, well, okay, I can do this with a calculator very easy, but later on when you do your challenge questions, you're going to have to do algebraic versions of this, and you won't be allowed to do use a calculator. So what I'm going to do, I'm going to get my number, and I'm going to do a prime factorization. So I'll do my factor tree, and I'll just do 2 because it's easy, but maybe I'll do 4. So let's divide it by 4. 664 divided by 4, and we get 4 by 2916. Well, this 4 can go to 2 and 2 again. My 2916, when I divide it by 4, will go to 4 and 729. This 4 will go to 2. My 729, let's just do a 3, will go to 3, 2, 4, 3. My 243 will go to 81 and 3. My 81 will go to 9 and 9. And my 9s will all go to 3s. And there we go. Good practice for our factor tree. So let's have a look what we've got. 1, 2, 3, 4 2s, and 1, 2, 3, 4, 5, 6 3s. So I know my prime factorization looks a bit like this. 1, 1, 6, 6, 4 equals to 2 to the power of 4 times by 3 to the power of 6. Now I'm going to break this up into 2 equal parts. So my 2 to the power of 4 can be like 2 squared and times 3 to the 3. But then I'm going to have another one of these. 2 squared times 3 to the 3. So look what I've done here. I've broken this up into 2 equal parts, okay? Because both of them have the same thing. They've both got up here a 2 squared, a 2 squared, and a 3 cubed, and a 3 cubed. And now let's work out what each part of this is separately. And that's like 4 by 27 times 4 by 27. And 4 by 27 is easy enough to do. You can work that out with some pencil and paper. It equals to 108 times 108. So our answer is actually just going to be the square root of this is 108, and we were just able to do that with some simple multiplications and knowing a little bit about indices. Just note, for this square root formula to actually work, I needed to have this 4 and this 6. They had to be even numbers because I needed to break the 4 up into 1, 2 here and 1, 2 here, and the 6 had to break up into 2 3s because when I times them back together they combine to be the 4 and the 6. Have a think about what the prime factorization would need to be if I can take a cube root. And while you're thinking about it, let's try to take a big cube root here now. So have a think about what the powers in my prime factorization actually need to be for this cube root to work. Alright, so now we've done it, or now you've hopefully had a think about it and pause the video. Let's do a factor tree again. So big number 5000, but you can see that we can break this up pretty easily. 1000 because it's got 3 zeros on the end, and 1 5 6 2 5. Now 1000 is 100 times 10, and this, well, I can see 5's a factor, so let's just get 5 out and do the division. And 15625 divided by 5 is 3125. I feel like I could have definitely taken a bigger factor out of it than that. So 100 is 10 times 10. This 10 here is going to be 5 times 2. It's done. Let's just do these 10s quickly now. 5 times 2, and it's a better line there. 5 times 2. This 5's already done, so let's get a 5 out of this. I'm sure I could have gotten a better number out of this. 5 and 6, 25. Divide by 5 again. 5 and 125. Divide by 5 again. 5 and 25 and 5 by 5. Alright, so let's count up our factors. Let's first get our 2's. So we've got 1, 2, 3 2's, and that's it. So we've got 2 cubed. Now let's count up our 5's. I've got 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we've got now times by 5 to the power of 9. And if you guessed before that both of these powers needed to be multiples of 3 to do a cube root, you guessed right. So we're going to break this up into 3 equal parts. So 2 times 5 cubed times 2 times 5 cubed times 2 times 5 cubed. And you can see there's 1, 2, 3 things I'm timing together, and 2 by 5 cubes, of course, 250, 5 cubed being 20, but the easier way to work it out is go 2 by 5 is 10, and then 5 by 5 is 25, and 25 by 10 is 250. And there we go, guys. We've got the answer. The cubed root of this is equal to 250. Giant cube root, no calculators needed. Alright, on to our next thing, our algebra review. Or preview, we haven't technically done algebra yet. So, the first one, 2 times x times 3 times y. Remember, if I write 2x next to each other, it just means 2 times x. But let's just put things in a nicer order now. That's 2 times 3 times x times y. Well, okay, but I know 2 times 3 is 6, so that's 6. And xy, when I'm doing my algebra, I don't need to write my times signs, so it's just 6xy. Next one, 5a minus b plus b. Here's something interesting. So I've got minus b plus b, or plus b then minus b. If I have plus b and minus b, well, they just kind of cancel out because we had a b and then we took away a b. So what we can do is we can actually just draw a little line through the b's to show, oh, they've cancelled out, and the question's just 5a plus a, which is 6a. Alright, third question, 7pq all squared. Well, that just means 7pq times 7pq, but that's just 7 times p times q times 7 times p times q, or 7 times 7, because I can write this in any order if I'm just timesing them all, times p, oops, it's a times p, times q, and put that all back together, that's 49 p squared and q squared. Done. And of course I can change the order that I'm writing things when I'm timesing them, because if I have, well, 2 times 3 or 3 times 2, they're the same thing, so I can swap around the order when I'm doing my multiplications. Alright, so it must be time for our puzzle. Our puzzle today is I want you to work out, is there a limited or a finite amount of prime numbers, or is there an infinite amount of prime numbers? Because after we get to really, really huge numbers like a trillion, well, there's so many smaller numbers than a trillion, it's got to have a factor in there somewhere. So if numbers get up high enough, will we actually run out of prime numbers and they'll all turn into composite numbers? Or will I keep being able to find prime numbers no matter how high I go? That's the question that I want you to have a think about, and think about how you can be sure and if you can prove that it's true. Alright, so that brings us to our homework. Our homework is from Cambridge Year 7, question 11E. So you're going to do from 1 to 7, A, C, E, and I've put 3 dots there. That doesn't just mean you do A, C, and E. It means you do A, C, E, G, I, K, and every second question in that manner. For question 8, I think the book says you're allowed to use a calculator, but I don't want you to use a calculator. I want you to do it the same way we did it in our worked examples. 9, A, C, E, and so on, the same as 1 to 7, every second one. Question 11, then all from question 15 to 18. That's question 15, question 16, question 17, and question 18. And don't forget, during your maths periods, your next maths period that you have, make sure you log into your classes Google Classroom, mark your name off, and you submit your homework into your classes Google Classroom for your classroom teacher to check. Okay, thank you very much.